video, I will present the notion of SubFinsler Lie group. In brief words, a SubFinsler Lie group is just a left invariant SubFinsler structure on a connected Lie group. After some simple discussions on this notion, I will remark that SubFinsler Lie groups are always geodesic spaces. Namely, every 2 points can be connected by at least a curve that realizes the distance. Let's see. Let's consider left invariant polarizations on Lie groups. So we fix G, connected Lie group, and G is going to be its Lie algebra. And for the moment, let's see it as setwise as the tangent at the identity of the group. So what are the polarization, the distributions, the subbundle or the tangent bundle that are invariant under the action of the left translations? So let me remark that, it's an easy remark, that there exists a one-to-one correspondence between the subspace, the vector subspace of the Lie algebra, and the family of tangent of subbundle of the tangent bundles that are left invariant. So let's call it polarization. And the correspondence is very easy, just it's the evaluation of the identity of polarization give a subspace, and this subspace determines the polarization, because if you have V a vector space, how can you determine the polarization? It's just, at any other point, it's just the push forward by the differential of the left translation by P at the identity of V. And I give you this as an exercise. Okay, check that it is left invariant and smooth. So smoothly depend on P. On the other hand, if you have some delta, then the inverse map is just the evaluation at the identity element. Okay. So if we want to fix left invariant polarization, we just need to fix a subbundle, a subspace of the algebra. Okay. Now, when is it that a polarization is bracket generating? So proposition is just very simple. Remark that, okay, let's fix a left invariant polarization. Then I claim that delta is bracket generating if and only if the subspace at the identity, delta 1, is not contained in any other subalgebra different than the whole Lie algebra. In other words, this space generates the Lie algebra. So let me write, so there exists no H inside G subalgebra such that it contains delta 1 and is not the whole Lie algebra G. Okay, let me spend some words about explaining why this result is true. It's very easy, but it makes us, it's a nice exercise to remember also what is the definition of bracket generating. Okay, so let delta k be the iterated spaces of delta, i.e. So remember, so this, okay, in general is not a subbundle, but in this case will be, because it's going to be left invariant. This by definition is the span of all possible brackets of vectors, vector fields. So one xl minus 1 xl when L is an integer less or equal than k, and xi's are sections of delta. In other words, vectors tangent to delta. Okay. So the fact that delta is left invariant implies that all these subsets are also left invariant. And therefore the rank at every point is the same. So posterior, so we will have that delta is equiregular. So we don't know yet if it is span, if it generates the Pauli algebra, but this is going to be equiregular. Moreover, even if delta is not bracket generating, so what we have is that the dimension of delta k 1, and instead of 1 I could put any other number because it's the same. This function as a function of k is not decreasing. It's not decreasing in k. And therefore, since the total dimension of the algebra is finite, then eventually there exists some k such that delta k is equal to delta k prime for all k prime larger than k. Okay. Now let's give a name to this. Let's call it, since I don't want to call star, k. Just let's call it delta star. Okay. Good. So this is always true. And on the other hand, if we have delta 1 as a subset of G, then we consider the smallest Lie algebra smallest Lie subalgebra of G containing delta 1. In other words, the Lie algebra generated by delta 1. Okay. My claim is that this subbundle delta star evaluated at 1, it gives this Lie algebra H. I didn't consider the small subalgebra, call it H, of G containing delta 1. So I claim that this fact is true, no matter if we have bracket generating or not. What is the reason? The reason is that we can choose we can choose a global frame for delta made of left invariant vector fields. Namely, we can take V1, Vm, a basis of delta 1, and we take xi, left invariant vector fields on G, such that at the identity, they coincide with Vi. Then what we have is that x1 up to xm, this is a frame, a global frame for delta. Now, the Lie algebra generated by the x1, xm, this is the Lie algebra generated by x1, xm inside G. This is equal to taking the sections of delta, taking the Lie algebra generated in the space of vector fields, and evaluating them at 1. Okay? So this is the Lie span of vectors fields tangent to delta. Okay, we saw this calculation already when we saw that taking a frame to calculating the iterated subbundle it's enough okay. And so since these are left invariant, the Lie algebra that generates as vector fields are left invariant vector fields, and they form frames of the iterated subbundles. So, okay, this was in general. Now, therefore, what we have is that the smallest subalgebra is equal to G if and only if delta generates the whole tangent bundle. So it's bracket generating. So this was the same of saying a definition that delta star is equal to TG. And that's the end of the proof. Okay, so now that we know what it is, a left invariant polarization on a Lie group, to do subRiemannian geometry, we need to fix a norm. And we will choose a left invariant norm. Okay, we choose now a left invariant I will write continuously varying, but that's going to be for free. Varying norm on delta. Okay, so of course we need to have continuously varying norm, but this will be for free, a consequence of being left invariant. Because actually, in a left invariant frame, the norm will be actually constant. Okay, so what does it mean? It means that we just need to choose a norm on the tangent at the identity. So it means choose a norm on delta at 1. And after you choose it, then what is the norm of an arbitrary vector v in P, delta P, when P is an element of the group? Since it's left invariant, it's just going to be the left invariant, the left translation push forward P applied to V, and this, and where this norm now is the norm at the identity, okay, at the subspace at the identity. Okay, so one can actually take this also to be the definition, right? So you fix this norm, and then you have a formula for the left invariant extension. Okay, so as an exercise, check that this formula defines a left invariant and continuous norm. Okay, right. Right, so now we are ready to do subRiemannian geometry. Okay, so GD will be a polarized, connected group with delta bracket generating. A left invariant. Then we're going to have a norm, left invariant norm on delta, and therefore the triple G delta and the norm is a SubFinsler manifold. Let's revise now what are the delta horizontal curves for this SubFinsler structure. So for simplicity, we fix delta 1, delta m, a frame, left invariant frame for delta. Then a curve gamma from AB into G is delta horizontal if and only if there exist functions u1, um from AB into R, integrable functions, for which the with the derivative of the curve is given by the sum u1t x1 at gamma t plus plus at t xm at gamma t. This is for almost every t in AB. So this is what it is, a horizontal curve. And now what is the norm of this vector? Okay? Remember, so this is a frame, so they all have the same norm. So we can push forward pull back this vector at the identity to know the norm. Okay. Moreover, the norm of gamma dot t, so this is the norm of this vector at the point respect to the norm at the point gamma t. But this is the norm at 1 of the pullback vector. So I pull it back by gamma t, the vector gamma dot t. And here this is the norm at 1. Okay. So I'll write the formula that I wrote just before as a sum of the ui's and differential gamma I gamma t, and this is equal to the sum of the ui's, the functions of t, times di, where, as before, the vi is just the value of the vector fields at 1. So this is a formula for the norm of gamma dot. And you see this is the norm at 1. So what we can think is that this is a basis of delta at 1, and we are just expressing the norm as the norm of the vector u1 to um. Let me write this. So hence, the norm of gamma dot t is the norm of the vector u1t umt in Rm, where on Rm we take the norm after identifying Rm with delta 1 via the ordered basis v1 vm. Okay, now how important is the norm? It's not really important up to by Lipschitz equivalence. Let me just remind something at this point. I'm going to use it soon. Recall that every two norms on Rm are equivalent, where equivalent means that the identity is a bi-Lipschitz map. Okay, so now that we have a norm of vectors, of horizontal vectors, we can define the length and therefore the distance. Okay, so let's put things together. So we call the triple G delta the norm a SubFinsler Lie group. Here, G is a connected Lie group. Delta is a left invariant bracket generating tangent subbundle. And the norm is a left invariant norm on delta. Okay. And after we have this triple, we can define the Carnot-Karateotel distance. So we equip G with a Carnot-Karateotel distance. The Carnot-Karateotel distance between P and Q is equal to the infimum of the length of gamma, such that gamma is delta horizontal from P to Q. Okay. Let me therefore remark that any two norms are equivalent. So here's a proposition. So every two left invariant norms on a polarized group defines CC distance functions that are globally by Lipschitz equivalent. In other words, so GD is the polarized connected group with delta bracket generating, and we have two norms, left invariant norms on delta. D is the CC distance function given by G delta, and the norm in D prime is the CC distance given by G delta and norm prime. Then the identity map from GD to GD prime is by Lipschitz. Oh. Good. Now let's discuss a simple property that SubFinsler Lie groups have. So every SubFinsler Lie group is isometrically homogeneous. Indeed, this is very simple fact, but every left translation is an isometry respect to the Carnot-Karator distance. And this is clear because each left translation preserves the bundle that is required to be left invariant, and therefore the family of sections of the bundle preserves the length and therefore the distance. Okay, and moreover, if I have 2 points P and Q in G, I can send P to Q by the left translation. What element? So if I left translate first by P minus 1, go to an identity, and then by Q, I go to Q. This map sends P to Q. So the space is isometrically homogeneous. And here's an important consequence of this homogeneity and the results that we saw about Carnot-Karator spaces. Every SubFinsler Lie group is a complete boundedly compact geodesic space. The most important part is geodesic space. So geodesics exist between any 2 points. Okay, more or less we saw already this fact as a consequence of being isometrically homogeneous, but let me just write some comments about this fact. Okay, so every SubFinsler Lie group is homogeneous. We just discussed it, and it's a length space because Carnot-Karator distances are defined as infimum of lengths. Moreover, for some epsilon greater than 0, all metric balls of radius epsilon are compact. Why this is true? This is a consequence of the isometrically homogeneity, because what we know is that Carnot-Karator spaces have the same topology as manifolds. So if you fix a point and say the identity, then for some epsilon ball, the closed epsilon ball is compact. But then, because of homogeneity, any other point has the epsilon ball that is compact. Okay, so metric closed metric epsilon balls are compact. And then we saw, when we were revising the metric geometry, we have this Hopf-Rinow theorem. I'll put a link in the description of the video where we're discussing this theorem for CC spaces. We have that the space is geodesic and also like boundedly compact and complete. Okay. Good. So SubFinsler Lie groups are geodesic spaces. Now, what can we tell about the geodesics? It's easy to see that geodesics between some pairs or some pair of points might not be unique. Already in the Heisenberg groups, this happens. However, even in the case when the norm comes from a scalar product, and hence we are in the presence of a subRiemannian structure, we do not know if geodesics are smooth curves. In the next videos, I will discuss more this problem. If you liked the video, you can let me know by clicking the like button. This will also suggest the course to other people. If you want to see more videos on subRiemannian geometry, please subscribe to the channel clicking below. Bye.